Assalamu alaikum. Welcome to the lecture series for CSS Physics. I am Usama Maud and I'm going to discuss the first section of paper 1 of CSS Physics syllabus, and its first subtopic is vectors. And today I'm going to discuss some basic concepts related to the vectors, and the remaining things we'll discuss in the next lessons. So vector, actually it consists, physical quantities can be divided into two categories: vectors and scalars. Scalar is a quantity which can be represented only with a magnitude. For example, the mass, length, time, temperature, volume, density, and there are many more. Vector is a quantity which can be represented with magnitude as well as direction. Without direction, it has no meaning. For example, the force, velocity, acceleration, displacements, we have to describe these quantities with certain number as well as the direction. Mathematically, a vector can be represented using this symbol. These are the three components. And graphically, a vector is represented by an arrow. See, this is an arrow. And the length of the arrow, it actually tells us the length of this line arrow. It actually gives us the magnitude of the vector. See, this is the magnitude, and magnitude can be calculated using this formula: x component square, y component square, z component square, then overall square root. So this is the length of the arrow, and the unit vector is actually the direction vector. Unit vector of related to any vector is actually gives us the direction related to that in that given vector. So a unit vector is usually represented by this a cap. It has the same direction as the given non-zero vector, and it can be described like this. So in general, you can visualize that a vector, it has two things. It has a magnitude which can be represented like this, and it has a direction which is represented by a unit vector. So unit vector can be calculated by this like this: a vector divided by its magnitude. For example, this is a vector: 1i, 1j component and 2k component. I, j, k, I hope that you already understand that these are the unit vectors along x, y and z directions. You have already studied in your college level physics and mathematics course. Magnitude can be calculated like this, and a vector divided by its magnitude, so this would be the unit vector. Now this unit vector, if you calculate its magnitude, it would be 1. It only gives us the direction in the of this vector a. Equal vectors, two vectors are equal if they have the same magnitude, equal magnitude and same direction, so they have their equal vectors. Negative of a vector is actually parallel to the original vector but opposite in a direction. Zero vector means a vector with a zero magnitude. Position vector of a point with respect to origin is OA vector. Now you can consider according to this diagram. For example, this is origin O, this is point A. So whatever is the point, for example, this is 3, 2 and 1. If you write this 3, 2 and 1 in vector form, so this is the position vector of A from the origin, and we can represent like this. Direction cosine. Any vector can make three different angles with x-axis, because any vector can be represented like this: these three components along x-axis, along y-axis and along z-axis, and whatever is the angle the vector A makes with a x component, and with the y-axis means the y component and z component. Using this simple concept of cos of angle, adjacent side over hypotenuse, we can write three different cos for three different angles along x-axis, y-axis and z-axis. So in general we can rewrite this whole equation in terms of ax, and when we substitute the value of ax over here, that can be written as a cos of alpha. Similarly for ay, we can write a cos of beta. For az, we can write a cos of gamma. Now this is vector a, and if we divide by magnitude of a vector a on both sides, over here as well as over here, so a over its magnitude is actually the unit vector, and on this side the a is gone. Now you can see that this is simply the unit vectors, cos of alpha I, cos of beta j, cos of gamma k. Or we can also write it in this form. Say this is cos of alpha, cos of beta, and cos of gamma, right? So if we take the modulus on both sides, so the modulus of unit vector is 1, and cos of alpha square, cos of beta square, cos of gamma square, this is also equal to 1. Vector product can be of basically the two types, the scalar product and the vector product. But if we have a simple vector, any other vector, for example we have some vector like this, okay, and we want to multiply it with a scalar number. For example, we multiply it with say 2. So whatever is the length of this vector, its magnitude, and we can multiply it by 2, so the resultant vector will become 2 times of the original vector, right? So our new vector 2l would be something like this. If this is l, so let me write it again. For example, this is vector l, and the 2 times of l is double of the original vector. It's in the same direction but doubles the magnitude. So when a scalar and a vector multiply, so there is only a change in the length. However, when a vector multiply with a vector, so there are two different type of products. One is known as the dot product, other one is known as the cross product. Dot product is a case when two vectors multiply in such a way. Look at this diagram. We have this vector b and this is vector a. See this part from here to here, we can say that this is a horizontal or component of a, or we can say that this is the projection of a in the direction of b. So when we multiply projection of a in the direction of b with b, that is actually the dot product. Similarly, if we take the projection of b vector in the direction of a, which is, we can let us represent by this yellow line, this is the projection of b in the direction of a, right? This b vector and its adjacent component, its horizontal component. So this would be b cos of theta into a. In both ways we shall get the same value. So either you multiply b dot a or a dot b, so that's why the scalar product is commutative. And if we write the a vector in component form, for example ax, ay, az, and b vector in component form bx, by, bz, so by using this formula we can get this simple expression. X component will be multiplied y into y, z into z, and you add them, that would be the dot product. Similarly, we can open this formula, a dot b plus c, so it would be a dot b and a dot c. Few interesting properties related to the this dot product, that this theta can be 0. It means that a dot b would be maximum, and if theta is 90 degrees, this is the case when when two vectors are perpendicular. So the a dot b, the dot product, would be 0, and if the angle is 180 degrees, in that case A dot B would be negative, right? So negative, very easy example for this negative is force of friction. Friction is always opposite to the displacement. So displacement is toward right, force of friction is toward left, and it will always decrease the energy, right? Similarly, for the simple example, for when the angle is theta, we can think about a case when an object is moving on the circular path. For example, like this, an object is moving on a circular path like this, and its force is always acting toward the center. So force is always toward the center. Okay, in this case the displacement is always along the tangent. So we can say that this is the displacement, and this is force. Let us write it as force, and this is displacement, and the angle between these two is 90 degree. So that's why the centripetal force does not do any work, because the angle between force and displacement is 0. Cross product or the vector product. Uh, when we have two vectors, so the cross product can be calculated by this expression AB into sine of theta, and its direction is perpendicular to the plane containing A and B. So we can simply use this right hand system, that if we turn our right hand fingers in such a way that it represents the order of multiplication from A to B, so the thumb will represent the direction of resultant vector, and if the order is opposite, B to A, the resultant direction would be different. So the magnitude wise, A cross B and B cross A can be same, but vector direction has been changed. So they, in general, we can say that A cross B and B cross A, they are non-commutative because their direction is opposite to each other. Right. Now, similarly, for the scalar triple product, mean a cross product of two vectors is multiplied with another vector. So this is a scalar triple product, and its result is actually a number which represents the volume of this parallelepiped. So this is the volume of the parallelepiped, and in case this volume is 0, if this scalar product is 0, it means that this A, B and C, all these three vectors are in the same plane. In that case the volume would be 0. And also if we write it in any order, so their answer would be same. Vector triple product is slightly complicated. A cross B cross C can be written as A dot C, this is a dot product of A and C, then into B. So this is a scalar number. A dot C becomes scalar, it's just a number, then multiplied with B, and then minus A dot B. Now again this is a scalar, it becomes just a number, then multiplied with C, then their total would be the resultant vector, right? And its proof is slightly complicated, and we shall discuss it in the next lecture. I hope you understand these basic concepts. In the next lecture we shall discuss some past paper questions, and over there we shall prove the same identity as well. I hope you understand these things, and if you have any question, any queries, you can write in the comments. I shall include these your comments and for the next lectures as well. Thank you.